On the night of March 24, 1989, the Exxon Valdez navigated through the frigid, pristine waters of Prince William Sound. Below its decks sat 1.26 million barrels of thick, unrefined crude oil. Up on the bridge, the safeguards governing that massive cargo were breaking down. Captain Joseph Hazelwood, who had been drinking earlier, was not at the helm. Navigational control fell to a severely overworked and fatigued third mate, while shoreside radar controllers completely lost track of the vessel. When the ship drifted out of the shipping lanes and struck Bly Reef, there was no secondary defense. The Exxon Valdez was a single-hulled vessel. One single piece of steel separated the oil from the ocean. The reef sliced open 8 of the ship's 11 cargo tanks. Immediately, 11 million gallons of petroleum flooded outward. A fatigued crew and a thin layer of steel were the only things protecting a delicate ecosystem. When both failed, the Alaskan coastline was subjected to a sudden, massive shock. The initial response cost vital hours. Alyeska, the pipeline consortium responsible for the cleanup, had a contingency barge sitting at the terminal, but it had been unloaded for repairs. Crews had to manually load the heavy equipment back onto the barge before they could even set sail. By the time the equipment arrived, a severe windstorm swept through the Sound. The violent weather overwhelmed the mechanical skimmers and floating containment booms, pushing the slick aggressively toward the southwest. Looking at the tracking map, the sheer scale of the failure becomes clear. Over the next 8 weeks, the heavy crude traveled hundreds of miles, contaminating the Kodiak archipelago and reaching deep into the Alaska Peninsula. At the time, scientific consensus treated oil spills strictly as acute, surface-level events. The response focused almost entirely on the visible damage. Crews scrubbed the rocky beaches with high-pressure hoses, attempting to save the seabirds and harbor seals actively smothering in the slick. Treating the surface of the coastline missed the larger threat. While responders blasted the rocks, a silent disaster was sinking rapidly out of sight. Traditional mechanical methods and chemical dispersants were highly inefficient in Alaska's frigid, rocky environment. Responders needed a different tool to break down the oil coating the shorelines. They turned to biology. Certain indigenous marine bacteria naturally use petroleum hydrocarbons as their primary source of carbon and energy. They literally eat the oil. The problem is a biological bottleneck. To consume the thick crude, these microbes also need nitrogen and phosphorus. In the nutrient-poor waters of Prince William Sound, the bacteria were starving, and the natural degradation rate was agonizingly slow. To bypass this bottleneck, scientists used a technique called biostimulation. They applied slow-release fertilizers directly to the contaminated shorelines. This gave the microbes the exact nutritional balance they needed to rapidly reproduce and attack the slick. Once supercharged, these microscopic engines tore apart the complex toxic hydrocarbon chains, metabolizing them into harmless carbon dioxide, water, and basic biomass. Leaning into the ecosystem's own biological mechanisms significantly accelerated the cleanup along the surface. However, even millions of microbes could not reach the crude that had already slipped underground. Tidal action had already pounded thick layers of oil deep into the gravel and cobbles. Cut off from oxygen and sunlight, the oil stopped weathering. It formed persistent subsurface reservoirs. The threat did not end when the visible slick washed away. It remained trapped in the soil, slowly leaching toxins into the water for decades. Water filtering through these rocks picked up polycyclic aromatic hydrocarbons, or PAHs. At concentrations of just 1 part per billion, these chemical compounds stunted the physical growth of pink salmon embryos and drove their mortality rates exponentially higher. The toxicity rippled upward. 2 pods of killer whales swam directly through the initial spill, resulting in massive casualties. Because they are highly social animals that rely entirely on older matriarchs to lead the pod, the loss of these key adult females caused a sudden, severe drop in reproduction. Species foraging near the shoreline, like sea otters and harlequin ducks, experienced decades of population decline. Their primary food sources, clams and bivalves, continually filtered the surrounding water, absorbing and storing the hidden toxins deep in their own tissues. The 1989 die-off was only the first wave of destruction. A more lasting injury followed the initial spill: the chronic, generational failure of marine life to reproduce in a poisoned environment.
The long-term data proved that a marine ecosystem cannot be completely scrubbed clean of heavy crude. Once the heavy oil hits the water, the chronic damage is locked in. The only valid solution is prevention. This realization forced regulators to eliminate the single point of failure that caused the disaster. The global shipping industry was ordered to phase out single-hull tankers entirely. Engineers introduced the double-hull design. Instead of one steel wall, an empty buffer space separates the ocean from the cargo. If a reef strikes, it crushes the outer layer, but the void absorbs the shock. The inner hull remains intact, securing the crude. For the people living in Prince William Sound, the battle moved to the courts. Assessing the invisible, lingering damages resulted in billions of dollars in cleanup costs, legal settlements, and demands for restitution over the next 2 decades. The Exxon Valdez demonstrated that nature possesses incredibly efficient microscopic tools to heal itself, but it also proved human engineering must respect an ecosystem's extreme fragility. The unseen scars of a spill remain long after the water looks clear.